Good morning, class. All right, today we are starting physics. So to start, we're going to do motion. So unit 1 will be based on motion, unit 2 will be forces, and then we'll get into energy. So those are really the basics of physics. So that's where we'll start. So if you're going to talk about motion, you have to start with distance and displacement. So that's what we'll be talking about today. Position, distance, and displacement. All right, the first thing we are going to do, if I can change slides here, let's talk about this thing called frame of reference. So if we're going to start any motion problem, we have to think about our place in our little world, our little universe, right? So and in order to do that, you have to pick a frame of reference. And this short video gives a good explanation of frame of reference and what it is, and gets your brain thinking to start class today. So it's pretty old, so the video quality is not good, but it's a good video regardless.
You're used to seeing things from a particular point of view. That is, from a particular frame of reference. And things look different to us under different circumstances. At the moment, things look You look peculiar.
You're upside down.
No, you're the one that's upside down.
No, you're upside down.
No, I'm not. He's the one that's upside down, isn't he?
Well, let's toss for it.
All right.
Okay. You lose. He's the one that's really upside down. You better come into my frame of reference now.
My frame of reference was inverted from what it usually is. That view of things would be normal for me if I normally walked on my hands.
This represents a frame of reference. Just 3 rods stuck together so that each is at right angles to the other 2. Now I'm going to move in this direction. You see the frame at the same spot on your screen, but you know I'm moving this way because you see the wall moving this way behind me. But how do you know that I'm not standing still and the wall moving? It was the wall that was moving. Now the wall has disappeared, and you have no way of telling whether I am moving or not. But now you know that I'm moving. The point of this is that all motion is relative. In both cases, I was moving relative to the wall, and the wall was moving relative to me.
All motion is relative, but we tend to think of one thing as being fixed and the other thing as being moving. We usually think of the earth as fixed, and walls are usually fixed to the earth, so perhaps you were surprised the first time when it was the wall that was moving and not Dr. Hume. A frame of reference fixed to the earth is the most common frame of reference in which to observe the motion of other things.
This is the frame of reference that you're used to. The frame is fastened to the table. The table is bolted to the floor is anchored in the building, and the building is firmly attached to the earth. Of course, the reason for having 3 rods is the position of any object, such as this ball, can be specified using these 3 reference lines. This reference line points in the direction which we call up, which is a different direction here than it is on the other side of the earth. And these 2 reference lines specify a plane, which we call horizontal or level. In this film, we're going to look at the motion of objects in this earth frame of reference and in other frames of reference moving in different ways relative to the earth frame. Well, let's look at a motion.
All right, so good example. Hopefully it gives you some idea of what frame of reference is. And the key that I wanted you to see in that short video was that all motion is considered to be relative motion. So it is movement relative to some other object. In our everyday life, like they said in the video, we tend to think of some things as stationary and things moving relative to that. So for instance, if you saw a car driving down the highway at 65 miles per hour, we would think of the car driving at 65 miles per hour relative to a stationary ground, right? So the ground is stationary. That means the car would be going 65 miles per hour relative to the ground. Now, the key here is if you wanted to make this a bigger frame of reference, you could. Now, what if we looked at that car and said, is that the absolute speed or velocity of that car? And the reality is it's not. So that car is going 65 miles per hour relative to the road, but the road is on the earth. The earth is spinning around in circles every day. And as we circle around each day, we're also orbiting the sun slowly. So in reality, that car is moving much faster than 65 miles per hour. But you don't really care about that every day. And if you're driving along the highway and trying to get to Plymouth in a short amount of time, all you care about is how fast you are moving relative to the ground beneath you. That's what you care about, so that's where you would limit your problem. That would be the frame of reference you would choose. Now, what if we wanted to fly a rocket to the moon? Could we think of the Earth as being fixed if we were flying a rocket to the moon? And the answer is no. We would know that the Earth was moving and the moon was moving relative to the Earth, so we'd have to factor all those things in. We'd need a larger frame of reference. So 99% of our problems, we'll just consider the Earth to be fixed, and that will be our frame of reference. But it's important to think about. So frame of reference is a system of objects that are not moving with respect to one another. Always choose the simplest one, and that's how you will start all problems. Okay, we're not doing the Mario Challenge this year. We'll save it for another time. Okay, if we're going to start motion, we need to start thinking of defining terms. Now, some terms are going to be easily defined by what we call a magnitude only. So 5 kilometers. 5 kilometers is considered a magnitude only, and that's considered what we're going to call a scalar. So in math, you might think of like a line segment as a scalar. So 5 kilometers, line segment, scalar. Now in motion, we got to think a little bit deeper than that. We need more definition than that. So is that 5 kilometers in this direction, or is that 5 kilometers in that direction? That would make a difference, correct? So we need to add direction to this magnitude. So that brings us to a vector. A vector has magnitude, 5 kilometers, and direction, east. So driving 5 kilometers east is very different than driving 5 kilometers west. So in motion, we have to define things as well as we can. So we use vectors. So we're going to use vectors for motion, for forces, but other things are going to be scalars, like energy is a scalar. You can have energy or no energy, but you don't have energy in a direction, correct? So we're going to have both scalars and vectors this year, but it's important to know that they are different and there are differences between them. In this unit, our first scalar vector comparison is going to be distance and displacement. So distance is a scalar. It's the length of a path taken between two objects. So if it's just the length of the path, we are not going to care about its direction. So if I were to go from point A to point B, I could take whatever path I wanted, right? So the length of that path would be my distance. So if I were to walk that path to get from point A to point B, it would be distance, and that's a lowercase d. If I were to want to know my change in position, which is what displacement is, what is your change in position? You have to know the straight line change in position. And if I went from A to B, there's a very definite direction I would have traveled, correct? So this is a terrible arrowhead, but we'll go with it. Your displacement, delta x, would be a completely straight line path from A to B, and that would be your ultimate change in position. So distance is lowercase d, it is a scalar. Displacement is, now we're going to get some terms here, delta, this triangle is called delta x, which is a vector. Okay, what does delta x mean? Delta means a change in. So that's probably something you will want to know. So delta means a change in. And in this case, we have a change in x position. So we have delta x, that's a change in the x position. You could also have a displacement of delta y, and that would be your change in y position. You could have delta z, that would be your change in z position. All those would be fine. Delta x, we usually keep things in the x dimension for our formulas, so that's why we list delta x. So a change in position means you could find that, right? So delta x, a change in x, could be your position x final. That's what that F means. So this is position final minus your position initial, right? Or initial position. So anytime you have a delta x, you can do final position minus initial position, and that will get you your correct displacement. You could also have other things, like you could have delta t, change in time, right? Delta means change in, t means time, so that would just be your t final minus your t initial. Final time minus initial time. You could do that as well. All right. Why is distance a scalar and displacement a vector? If you look at this distance path, you can see that the direction it is traveling is ever changing. So you could never assign a direction to that distance because it's always changing. So that is often with scalars, is they don't go a certain direction. There is no absolute direction you could assign to them. But this vector, and if I had drawn it perfectly straight, would have a very definite position, and we could specify that. So that means it's a vector and it's going in that direction. Here's some examples. So example 1, we have another A to B, and you have your displacement down here, which is a vector, and your distance. So I'll get that out of here, right? Your distance could be some number. Say, we'll make up some numbers here. Your distance would be 8 kilometers. Again, you could not give a direction to it, even if we gave a little compass up here. North, south, east, west. What direction would that person be traveling on this path? The answer is all different kinds of directions. So we can't give a direction to that. So we'll just say the distance is 8 kilometers. Now, displacement, let's make up a number here. First off, what's going to be bigger, distance or displacement? In this scenario, displacement will always have to be a shorter path or a smaller number. The magnitude will have to be smaller because it is the straight line path, which is the shortest path between A and B. And for sure, distance traveled a longer path than that. So your displacement is going to be something like 6 kilometers. Now that's a magnitude. We have to now add a direction to that to make it a proper displacement. So what would be our direction? Using this compass up here, I could say we traveled 6 kilometers east. Beautiful. Now, you could also do something like 6 kilometers in the positive direction. We'll see this later on today, but you can also specify directions by positives and negatives, and that helps you do math sometimes. So we're going to see that later today, but something to be aware of. A positive and a negative can also be a form of a direction. All right, next example, walking around the block. So if I were to start here, and I want to take a trip around the block, so I walk 1 block north, then I walk 1 block east, then I walk 1 block south, then I walk 1 block west. Okay, what would be my distance traveled? So what would be the distance I walked? So I walked 1, 2, 3, 4 blocks, right? That's how far I walked. I walked 4 blocks. Now, what would be your displacement? Your change in position from your starting and ending point. Well, if I started here and I ended here, what is my change in position? 0. There is no change in position, so you would have a displacement of 0 blocks. That's also very possible. So just something to think about as we go along here. We don't get to watch Bo Jackson this year. If you want to go watch it, I'll post the notes. You can watch Bo Jackson, and he has a very different distance and displacement in this video. So he goes for a 100-yard run. So his run is 100 yards in the positive direction, but in the video he takes a much longer route. So his actual distance traveled is different than that, which is normal. All right, how do we add vectors? So I'm going to do 2 examples here. I'm going to do a linear example, so 1 dimension, and I'm going to do one that has 2 dimensions. Now, why do we have vector addition? So say we had 5 meters plus 2 meters, just scalars, distances. We could say we had a total of 7 meters that we traveled, right? So if you're looking at distance, you can just use regular addition to add scalars, right? So scalars can be added using normal addition. So displacement, though, I don't think that's going to work as well. So if we do it visually, if I said we went 5 meters this way and then went 2 meters back, is your displacement 7 meters? The answer is no. Your displacement would be 3 meters, right? Your change of position from here to here is only 3 meters in the positive direction. So your displacement is plus 3 meters, not 7. So there's a difference here. Here we used regular addition. This is just normal addition. Oops. And anytime you have a scalar, you can use traditional addition. If you have vectors, you cannot, because they don't go in the same direction. If they were all in the same direction, you could probably use standard addition and just keep your direction going with it. But they don't always go in the same direction. So you have to use something called vector addition. So that's what we will be doing here. So how do you do vector addition? So let's clear this screen so that we can do this. All right, so vector addition. All right, let's do let's do 10 meters north plus 8 meters south. Okay, so we have for sure two vectors, so we can't just do 10 plus 8 because that would say 18 meters, and that is not our displacement. That's not how far we are from where we started. So to do vector addition, you're going to draw it out. It's a graphic thing. You have to draw these visually to be able to do it. So what you're going to do is you're going to draw one of the vectors. Now here's a odd thing, but it doesn't matter which one you pick. You can draw them in any order. You can add them in any order. It doesn't matter. But I'm going to pick 10 meters north just because that's what most people want to do. So if I take 10 meters north, start from that point, and I'm going to go 10 meters north. So I have done step 1. I've drawn my vector. Step 2, start the second vector at the head of the first vector. This is the most troublesome part. A lot of people draw 10 meters and then want to come back here and then draw 8 meters south. That doesn't work. You cannot do vector addition that way. So let's erase that. That is wrong. If you want to add, if you have 10 meters and you want to add 8 meters south onto that, you have to recognize that you've traveled 10 meters and you are now here. So when you add 8 meters onto it, you have to start here. Now I'm going to draw it right next to it just for clarity's sake, but I need to start my vector at the end of my first vector. So my second vector starts at the end of the first vector. It's called tip-to-tail technique. So we start our 8 meters south here. And now we're going to draw our second vector, which I just did. And then step 4, draw the resultant vector from start to the finish. So here was our start, and here is our finish. I'll draw it right next to it for clarity. So from the start to the finish, we need a vector. I usually do these as dotted lines. I'm going to call that R, or delta Y, because we're in the Y dimension, right? So this, our R is our displacement, our delta Y. So why did I call it R? Because your resultant vector, anytime you add two vectors together, is going to be, the vector sum of two or more vectors is going to be called a resultant vector. So this little vector is the resultant vector. In math, you'll call it a resultant vector. In physics, you'll probably just call it your delta Y, which is fine. What is my delta Y? It is going to be 2 meters. Now you have to have a direction here. The direction in this particular part is shown by the arrow, but down here I'm going to show it with words. 2 meters north. And that would be your final answer. Beautiful. Right? Not too bad. You can also do these at right angles. So let's do another one. Let's do 5 meters north plus 5 meters east. So what would that be? We're going to start by drawing our first vector. So here's a vector. We're going to draw that to be 5 meters north. Then we're going to go to the tail of this one and draw our second vector, 5 meters east. Now we are going to, step 4, draw the resultant from the start to the finish. And it always points to the finish. So you should have kind of 2 arrows there. And this is your R, your resultant vector, which will be our, let's call it our delta x, our change in x position. So, beautiful. We have done vector addition. Now, could we find that actual value? Yes, we could do Pythagorean theorem here and find that value. Could we even go farther and find this angle Yes, we could use trig and find that angle. We won't have to do that, but you probably need to use Pythagorean theorem and have some general idea that this is going northeast, correct? That's shown by your resultant vector. All right, so let's practice this a little bit. Now, the first practice we're going to see is an example by Mythbusters. So Mythbusters took a truck, and they drove, let's draw a nice little truck here. You guys don't know this yet, but I'm a wonderful artist. You're going to love my beautiful drawings all year long. All right, we got a truck, and it's going this way, and let's pick a speed. 10 miles per hour. Now, what Mythbusters is going to do is they put a little soccer ball cannon in the back of this truck. And from that soccer ball cannon, they're going to shoot a soccer ball out this way at 10 miles per hour. Now, these speeds are just made up, but they provide a little bit of clarity here. So we have a truck driving 10 miles an hour this way and a soccer ball being shot 10 miles an hour that way. So what we are doing is we are adding two vectors. We're adding 10 miles per hour left plus 10 miles per hour right. So let's do that. Let's draw this out. So we'll take our first vector, and I'll do the left one first. So we go this way, 10 miles per hour. Now you'll notice one weird thing here. I'm not using displacements right now. I'm using velocities, which is also a vector. You can add any vector this way. So velocities, you can add them the same way too. And we should get the final velocity of the soccer ball. So we have a truck going 10 miles per hour this way. We're going to add the second vector on. So that starts at the end of the first vector. And then we have 10 miles per hour right. So what's our change in velocity? What's our resultant vector here? 0, correct? So if you were able to drive a truck at some velocity this direction, 10 miles an hour, let's say, and then shoot a soccer ball out the back at exactly 10 miles per hour, then what should the soccer ball do? Well, the soccer ball should just stay in place. It should not move at all, at least in the horizontal position. It'll probably fall down due to gravity, but back and forth, it should not fall at all. So let's see how they did.
I have a feeling that we are very close to a perfect demonstration. We're going to see that ball drop.
With the forward and backward momentum matched as close as they're going to get it, the pressure's on Grant for a perfect release.
I don't know about you guys, but that looked pretty good to me. Let's check the high speed.
It really looked good to the naked eye, but the judge in this case is the high speed.
Oh my God, it's like a cartoon. It's just in the air, it stops, and it just falls.
Look at that. I mean, look, it doesn't move at all. It's going straight down.
Woo! We did it! We did it! Yeah! Vector addition! Yeah! We canceled out velocity!
After 3 days of suffering, that single shot brings the myth to an end.
I can't be happier. We actually got the speed of the car to match the speed of the soccer ball, and we got a perfect straight down drop.
Ladies and gentlemen, the laws of physics are still hard at work.
So beautiful. Vector addition does work. Not something we think about every day, but it's something you do have to think about when you're doing physics problems. Okay, let's do 2 examples, and then we're done for the day here. So, a jogger runs 12 blocks north and then runs 8 blocks south. So we want the distance traveled. So distance traveled, you can just use regular addition, right? 12 blocks plus 8 blocks. The distance traveled by this jogger would be 20 blocks. When you have scalars, you can use regular addition, and it works nice. So what is the displacement of the jogger? Okay, so now we need displacement, which is a vector. We'll have to use vector addition. So let's draw that out. So I'll start with my 12 blocks north. And then we're going to go 8 blocks south. Notice how I started my second vector at the end of my first. And then we are going to do our resultant vector, which will be arrow from the start to the finish. So always point towards the finish. So this would be your resultant vector, which is your displacement. Call it delta x. So what is our delta x there? Our delta x, our displacement, is going to be 4 blocks. Now we have to put a direction here. The 12 was going north and the 8 was going south, so we're going up the same as direction as, get out of here. We're going up the same direction as the 12 blocks, so this is going to be 4 blocks north. So that is our final answer. Anytime you want to second guess this stuff, if you are asked for a scalar, make sure you have a scalar. And if you're asked for a displacement, that's a vector, make sure you have magnitude, 4 blocks, and direction, north. Beautiful. Now let's try one not in 1 dimension, in 2 dimensions. A boat travels 3 kilometers north and then turns and travels 4 kilometers west. Okay. Find the resultant vector graphically. So we're going to graphically add those 2 vectors together. So I'm going to do this twice so that you can see that the order does not matter. So we start here and we go 3 kilometers north. Now, I showed this on a previous screen, but I pretty much always just use this little compass on my sheet of paper. So if I'm going that way, I'm going north. I don't know why that keeps popping up. I apologize. So 3 kilometers north, and then turns and travels 4 kilometers west. So we're 3 kilometers north, we're here, and now we're going 4 kilometers west. Your resultant vector would be from the start to the finish. So it would be a line directly between the 2 points, pointing to the finish. That is your R, your resultant vector, which is also your delta x, right? That is an R, although a terrible R. Okay, beautiful. So graphically, we have found our R, our resultant vector. But remember I told you, you can add these in any order. So let's try a different order and see if we get the same result. So what if I start here, and instead of going 3 kilometers north first, I'm going to show 4 kilometers west. Then I add my second vector on, which is 3 kilometers north. Add in your resultant, which is from your start to your finish. So always point towards the finish, and that is your R. Now, if you just look at those vectors, they are the same length and pointing in the same direction. So those 2 R's are exactly the same. You could show the work either way, and they're both correct. So we have found the resultant vector graphically 2 different ways, and they're good. So now we're going to find the magnitude of that resultant vector. So if here is our movement, our actual position change, we need to know the magnitudes, the actual length of that vector. So how can we do that? Well, this is a right angle triangle, right? There's no difference there between something that looks like this, right? So this looks a lot like math class. So if we know this side and we know this side, can we find this side? Well, maybe we'll call it C. The answer is yeah, you can use Pythagorean theorem. So you do a squared plus b squared equals c squared. So a and b are the two legs of your triangle, right? So 3 kilometers and 4 kilometers, doesn't matter which one's which. So 3 squared plus 4 squared equals c squared, which is what we're looking for, our magnitude of that outer part of your triangle. So 3 squared is 9, 4 squared is 16. So 25 equals c squared. What do we do now? Well, we want regular c, so we have to take the square root of this, which means we have to take the square root of this. And we get c to equal 5. Beautiful. So our actual magnitude of our resultant vector is our r magnitude is going to be 5. Now we always need a unit in physics. It was 5 what? Well, these were 3 and 4, but those are 3 kilometers and 4 kilometers. So our other leg of our triangle is going to be kilometers as well. So 5 kilometers. Beautiful. Now, if I want to add some definition here, could I tell you roughly what direction that r is going? Yeah, I could give you a rough idea that it's going northwest. So now you'd have some sort of magnitude and direction. Could I even go further and tell you like what angle it was going? I could. We're not going to go there, but if you want to take it further and find that exact angle that it was traveling, you could do that as well. And that's all possibilities. So that'll be for another day. All right, let's review. We learned that a scalar is a value with magnitude only, and a vector has magnitude and direction. And the scalar and vector we were talking about today were distance and displacement, which we are going to need to describe motion. Then we did vector addition. We did it in 1 dimension and in 2 dimensions, and you should be able to do both. All right? Have a wonderful day. I will see you guys in class.